I'm Vasco Cavina from Scuola Normale Superiore in Pisa, and I will talk about exact requirements for battery-assisted qubit gates. So this is a work that I did in collaboration with Riccardo Castellano and Pavel Sekasky from the University of Geneva, Martí Pernau-Lobé from the University of Barcelona, and Vittorio Giovannetti from Scuola Normale Superiore. And the paper is currently under review on quantum. Okay, so first of all, I want to give a brief introduction of the connection between batteries and gate implementation. Quantum batteries is a very active field of research in the last years, and there was a focus on the speed of charging of quantum batteries. So obtaining a quantum advantage using quantum devices in the speed of charging. And there are many results about this, mainly due to collective effects that you can have in this kind of batteries. But what is interesting for us is that there was focus on batteries as repositories of average energy. Okay, this was basically the definition of battery. So the first question that we want to ask, and that we will kind of answer during this presentation, is average energy the only resource that we can store in a quantum battery? And also, from a practical point of view, how can batteries help quantum computation? And of course, about this we had already the nice presentation by James. What we will do to tackle this problem is to basically use an operational definition of a battery that basically is borrowed from resource theory. So what we want is to perform a non-energy preserving gate that is just a unitary operation Vs that doesn't commute with the Hamiltonian of the system S. And we want to implement this operation by coupling our system with the battery, performing a global operation that now preserves energy, and then we will look on our system, what's happening on our system, and we want to obtain that at the reduced level of the system, we are as close as possible to the gate we wanted to implement. So from a more formal point of view, when we couple a system with a battery, what we are performing is an open system evolution. So we couple the system with the ancillary degrees of freedom, we perform our operation, and then we trace away the battery, okay? So this will be a completely positive trace-preserving evolution on the system S that we call phi, and we want this phi to be as close as possible to the gate we wanted to implement. Of course, this optimization can be done on the specific coupling between the system and the battery and on the state of the battery that should be chosen properly. Of course, this is not a trivial question because, as you know, CPT map obtained after coupling the system with an environment is typically not even unitary. So we have to engineer the coupling and most of all the initial state of the battery in order to ensure this condition that is approximately unitary and very close to the gate that we want originally to implement. Okay, so now I can, again, based on this framework, we can already mention some results in the literature that basically highlight that energy is not the only resource in this context. For instance, in these two papers by Kiribella and co-workers and by Tajima and co-workers, they considered exactly this problem, and they identified some bounds for the precision in gate implementation by using auxiliary systems. So you can see the precision is measured in terms of the error. I don't think you can see the pointer. By the way, is the one underlined in red. That's the worst case infidelity between the gate V and the map phi. So it's a measure of how much we are close to the gate we want to implement. And 1 over the square root of this quantity is a good measure of precision. These two bounds tell us that a good battery, a good auxiliary system that you use to implement your gates is very good if it has a lot of average energy, and this is basically the result of the first paper. But it also needs a lot of QFI, quantum Fisher information, relative to the Hamiltonian of the battery itself. And quantum Fisher information is a measure of coherence. So a good quantum batteries that allows you to perform generic gates with high precision should have both energy but also coherence measured in terms of quantum Fisher information. So we will basically build on this framework and extend these results. So in our work, what do we mean by precision in gate implementation? We will measure it in terms of the choin fidelity. The choin fidelity is a channel proximity quantifier that can tell you when two gates, two generic CPT maps are close to each other. So it's not very interesting, the formula itself. We choose this measure because it's kind of simple when one of the two maps is a unitary evolution, like in this case in which V is a unitary gate. Okay, so in terms of this choin fidelity, we will measure the error in the procedure of gate implementation, and this can be related with the worst case infidelity that sometimes is preferred. So the papers of Kiribella and Tajima, for instance, were using worst case infidelity, but for finite dimensional systems, the two are equivalent, so it's not really a big difference, and they are equivalent thanks to these bounds, and for instance, the first bound is actually a new bound that we proved. The standard bound with Fuchs-Van de Graaff inequality is with a d squared that is slightly looser. Okay, so we will assume that the system is a qubit and that the battery is a harmonic oscillator with the same gap omega. And also, in this case, as you know, basically a unitary evolution acting on qubit and oscillator that preserves global energy can be decomposed in effective two-level systems in which the energy is fixed. Okay, so we have only to understand how to choose these unitaries in these two-level systems, okay, in which you have a fixed amount of energy. And basically, this is the only freedom that we have in defining this unitary evolution. And how we choose it in such a way that these two-level blocks are exact copies of the gate we want to implement. So exactly equal to Vij, the elements of this inside these two-level blocks. Okay, so basically all of this is kind of forced. So the real optimization will be on the initial state of our battery, because these choices are kind of forced. I mean, a good battery is a battery that is infinite, of course, is better than a finite one, and also the gap should be always the same, otherwise your system cannot resonantly couple, because here we are doing an energy preserving operation. So basically, an harmonic oscillator is the best candidate, and the interaction, the choice of interaction, you can show that this choice in which every two-block unitary being equal to the gate you want to implement is also kind of the optimal choice. So the real optimization is on the initial state of your battery. So we write the choin fidelity, that is the measure of how much we are far from the gate we wanted to implement in terms of the initial state of the battery. So here beta n are the amplitudes of the nth level of the battery, okay, the nth energy level of the battery. And you can write the error in terms of this formula in which you have this, the first term is basically a discrete first derivative, and the second term is basically a discrete second derivative. And now we want to minimize over this preparation in order to obtain the best battery state, the one achieving the maximum precision. So this is kind of difficult to do in general, but what we can do analytically is to do this optimization in the limit of high precision, so when this epsilon is close to 0. This is basically the case that is interesting for quantum computation, because when you want to perform a gate, you want to perform it with fidelity close to 100%. Of course, it's not really useful to perform it with a fidelity of 70, 80%. So this asymptotic limit of high precision is the one that is more interesting for practical purposes and is the one that we can solve analytically. So what happens in this limit of high precision? We show that optimal battery preparations are smooth preparations, so basically are a choice, a family of states for which this discrete first derivative and this discrete second derivative become real derivatives, okay? So you have kind of to do a smoothing and to do a limit in which the smoothing parameter goes to 0, and you regularize everything. So I don't want to mention too much the details of this procedure, but basically the idea is that this amplitude should vary very slowly over basically the different energy levels, okay? If we do this procedure, we can express the error, the choin fidelity, as a function of a new quantity that we defined that is just basically depending on the preparation of the battery. And this quantity is this unitary defect that is just the integral between 0 and infinity of the derivative of this function psi, square modulus, and the function psi is just the regularized version of the basically amplitudes of the battery preparation. Okay, so how we can obtain here some bounds on the precision using this technique? What we can do is basically fix some resources in our battery and then optimize the precision for fixed resources. After we do this procedure, from the result we can extract new bounds in terms of these resources for the precision that we want to obtain. Some resources could be average energy, average squared energy, and number of occupied levels, okay, in the battery. Those are the resources that we consider. And now, as I was telling you, we want to minimize the unitary defect, that is maximizing the precision with fixed resources, and this can be done with Lagrange multiplier technique. So basically what we have to do is to write an action in which the first term is the precision, the unitary defect, and the second term is Lagrange multiplier times the constant resource. For instance, for the average energy and squared energy, you have an action that is much similar to the action of a particle in a one-dimensional potential, okay? And we show in the paper that the problem of finding the optimal states for fixed average energy can be mapped in the problem of finding a ground state of a one-side linear potential. Average square energy can be mapped in a one-sided harmonic oscillator, and number of occupied levels can be mapped in the ground state of a particle in a box. So basically, those are all textbook, and we can just use the solutions that we know from basic quantum mechanics. And in this way, we find optimal battery preparations, so the preparations that maximize the precision when you have fixed energy in the battery, fixed squared energy, and fixed number of occupied levels. And you find the asymptotic minimum in all the cases. From those results, since you know that they are the best state, so every other state has to do worse than them, you can derive 3 new bounds that are a bounds on the precision in terms of the energy, average energy of the battery, one in terms of average squared energy, and one in terms of number of occupied levels. So basically, these 3 things are all resources that are beneficial if you put them in your battery before coupling it with the system if you want to enhance the precision. Also, we find, again, the results by Tajima, the bound on the quantum Fisher information, but I didn't put it here because that was not new. Of course, is already in the paper by Tajima and Shirashi. So I want to conclude. So we express gate precision in terms of Choi fidelity and found a relation with worst case infidelity. After we introduced this asymptotic figure, the unitary defect, to basically understand the optimal states for gate implementation, and then we mapped everything in a 1D ground state problem, and from here we find the necessary conditions on the precision in terms of resources, energy, average energy, and so on. So just a last slide after the conclusion, I want to mention this work is mainly theoretical, of course, how to go toward a practical implementation of this result, because of course this is good in terms of resource theoretical approaches, but how these results are close to an application, okay? The first thing that we notice is that this approach, if you manage to transfer it in technology, can help you to bring down a possible source of error, not the imprecision connected to gate implementation. There are many sources of error, of course, like noises arising from control lines, noises in the readout stage, and so on, but there is a source of error coming from coupling your qubit to external degrees of freedom and performing the gate. This technique could possibly lead to bringing down this error, and a way to go toward toward implementation of this result is, of course, to realize, let me go back a lot, this kind of interaction that I mentioned. Okay, of course, James Cummings, Tavis Cummings are not like this. You cannot have like an interaction, a profile of interaction that is constant in n. Usually there is the square root of n in the frequency. So basically you have to do some engineering of this interaction if you want to bring this result to technological application. This is the only comment that I want to make. And with this, I thank you, thank you everyone for this. And I also want to suggest this other paper in which we study relative entropy of coherence as a resource that basically is complementary to this. Thanks.
Okay, we still have time for questions. Okay, go.
So this question is actually can be applied also to the talk by James. I'm not sure I understand if this actually applies to all implementation of quantum computing and qubits and gates, or is it a specific of the system and more specifically for energy level qubits? If I have degenerate qubits,
yes.
would it apply?
So the bound, this one apply to qubits. So if you want to basically, if you have an architecture in which you have to perform global operation only by doing local qubit operations, you have to apply, you can apply this bound. Of course, the error will accumulate, no, for every operation, but it's not optimal. So you can find better bounds when you have global operations, like you are acting on a bunch of qubits and you have degeneracies. You could find bounds that are better than this. So we are pretty sure that the bounds are can be improved if you are considering systems with degeneracies. And actually, this is a direction that we wanted to take. Also, yeah.
Even more specifically, if my single qubit is the energy levels are degenerate, it's like two holes are like the two levels are degenerate. So I apply a reversible unitary. Why would I need to spend energy? Why do I need?
No, exactly. This is in that case. Basically, this is all for. This comes from basically the resource theory of if you want asymmetry. And the symmetry that you have is exactly the U1 symmetry that is given by the exponential of the Hamiltonian. This all becomes trivial if the Hamiltonian is trivial, actually. So in that case, I think there... so if you still have a preferred basis, you should still have bounds in terms of the relative entropy of coherence, because that one doesn't depend on the eigenvalues. So this is my intuition about that. Of course, all the other bounds become trivial. The one bound by Tajima, the bound by Kiribella, our bounds, yes.
Interesting, thanks.
Do we have another question? Okay, otherwise we can thank Vasco.
Thank you.